That's Tri-State Catalysis seminar. And before I start, I would like to give greetings from our president, Dr. Jürgen Laderbeck. He apologizes for not being able to be here today. He had a prior engagement, and so he will meet us again at the next meeting at the 20th or 21st, which will be announced, of August, for a seminar. We have a speaker coming from Germany, from the University of Munich. I'm not exactly familiar right now with who it is, but Jürgen said that he will take over the seminar arrangements for a visitor to sit to me. Without any other news for the Tri-State, I would like to welcome Dr. Eric Grulke, our speaker for today. He was very gracious to agree to give a seminar today on 3D visualization of nanoparticles. And what that means is there is really hot off the press a new model available now to help us understand at the nanoscale the morphology and structures of nanoparticles. And I will give a very, very short intro why we're so interested in this type of model, and then Eric will take it from there. So please stay with me for just a little bit. Do I just push the enter here?
I think we're just going to just press the enter if you want.
Yeah. Cool. Go ahead. Actually, what we really need to learn is at the nanoscale how we can translate 2D images into a 3D model. When we have wires, like nanowires of gallium oxide, for example, some of us are better than others to try to get a 3D imaging of these particles. And there is a model now available that Eric will introduce, how we can then actually have a structure in our hands to translate what's happening at the nanoscale and see it at the more regular vision. Even at the nanoscale, this is a higher resolution TM, you can see that there is some depth to the wires, and we'd like to be able to get a little bit better handle on that. That's why we approached Eric and said, we're in the catalysis area, are very interested in this model. And even on an almost 2D system like this droplet, there are key features that we're interested in trying to further identify the depths and structures. Webs is another area where we would like to see this model being applied. And if you can see here, this is experimental facts versus theory. This is a SEM right here and over here of a nanoweb. And we're really clumsy at the moment without this 3D model, trying to visualize how this 3D system can be applied at the nanoscale. I'll show you what we've been able to do until now, and then Eric will surprise you with what's able with this model. A web, we visualize it like this. You have the first nano web layer, a second nano web layer that then gets superimposed, added to the first one, and then a third one will be added, and it will sit down on the earlier one and the fourth. And the models that we will then hopefully learn about today, and to see how catalyst particles are sitting on support structures, can be modeled with some software. So without going into any further detail, I'll let Eric take over.
Thank you very much, Ushi. I think Ushi has sort of described why you might want to use a 3D model. I guess she's got some more material here. Let me show you what we're able to do. I'm trying to remember which one. I think this is the one that we need first. Yes. There is some new software which was just announced in April, end of April this year, in which you can control TEM imaging so that you can do a series of scans and scan through the material, save those images, and then you've got a 3D representation, if you can then connect splines and so forth. So I've got really two parts to this. The first was provided by Alan Dozier, who's our microscopist, and we have the information on how this is done. So I'm going to take you through this, and then the next part is how you actually can make a 3D object from this scan, okay? Because that's what we've been able to do, and I can show you the results of that today. So basically, this is used to recover, it's called electron tomography. It's used to recover the 3D mass density distribution using a number of images taken in different directions, okay? So experimentally, what you do is you set up the TEM to take a series of images of your object, and usually you do a stage translation, that is, you compensate for the X and Y directions. So you can, and I'm going to show you some stuff where you rotate around the X direction, rotate around the Y direction. And you get, I think I can turn off my cell phone for my own talk, I apologize. Then basically, once we have these sets of images, we can export this information for a fine alignment and a reconstruction, and then they can send this to a visualization package for viewing and analysis. The company that does this is Synapse, and basically we are using some of the images that they were showing at the shows to sell their software. Basically, what you do is you calibrate X, Y, and Z stage movements in your TEM, and then let me show you a typical image. Okay, this happens to be, surprise, surprise, graphite particles. Okay, this is sort of like a soot, graphite particles, and these are all sort of attached together. And what's interesting is that these are different slices through the particles. This might be starting at the bottom of the nested particle, and then I take another slice through, and here it is. Now, so this, I'm just going in the Z direction going up and acquiring data. And what's interesting is when you look at this, it looks like it's hollow, right? Okay. And then you can see up the top, you know, you lose some structures. So these are just example structures, graphite particles, and that's the kind of image we get. Okay. Then there's some other automation stuff that's done, and they reconstruct it and they visualize it. Let me show you what this looks like. This is the file. This is part of the file that is generated. Here's Alan Dozier in the back of the room. Alan, do you have any comments about how they did this?
Well, the trick to the new system is the computer control over the microscope, and how the stage is completely controlled by the computer. And before, you know, all that had to be done manually, and it would take hours and hours. And now with the computerization, it becomes sort of a practical reality.
Okay, so that was a very short answer. Thank you.
Yeah.
That's good. Okay. And so these have been visualized by their package, and here's a different series of rotations of that, of this particular sample, and this is the one we built. And then, so we're actually sort of halfway through this process to try to demo it for ourselves. What we've done now is we've actually been able to manufacture a solid that looks just like this, but much bigger, so we can see it. We've also taken a picture of another material. Surprisingly, it's a carbon nanotube, and we would like to image that as well. And for example, here is the. See if I can get this to. No, I can't get it to go. Let me go back here. Here, I can get it to rotate. Basically, what this does is it really defines a material in three-dimensional space so it can rotate. If you look at this, and you've seen, this is sort of the carbon nanotube here, a big multi-wall, then here's two little skinny ones, and we hope that these bright spots are some iron catalyst stuck in there. Because what we'd really like to do, getting at the catalysis issues that Ushi was raising before, what we'd really like to do is be able to image through this particle, and then using the build software, where we're actually building a three-dimensional object, we can put colors and assign colors to different things. For example,
Can you run it again?
yeah, I'll run this again so you guys can see this again. Now this is the rotation. Let's see if I can get it to go here. And that's rotating. So I can rotate the solid in one direction, and the next slide rotates it in the next direction. So there's my three-dimensional solid I built from this series of schemes. So it looks like it's a robust image, okay? So now we go to the next piece. Well, fortuitously, about the time that Alan was saying, hey, we got new software, one of our fellows who does stereolithography says, hey, I'm looking for new applications of stereolithography. And so for some of you who don't know, stereolithography, and also there's another build technique that we use for this. Stereolithography is a way to take something like an MRI image, series of slices in MRI, put splines in three-dimensional space, and then build that material in plastic. So you've got a solid, okay? The new technology does the building with a powder and actually cements the plastic together with spray coatings which can be colored. And so you can actually, for example, one of the things we would like to do now is to build this thing, color the iron a different color from the carbon. So you can see exactly where the iron is, either by looking at the cross-section or not. So the hope is that we can now distinguish between these materials and get an idea of where is the catalyst sitting, how big is it, what's its morphology. Start to get at those kinds of questions, three-dimensional structure at the nanoscale, and blow that up so we can have some appreciation of it. Okay? So I think that's what we can show you in this series. Let's go to how you build this. So here's how you make solid models from this. Let's see, let's go to the slideshow. Okay. So basically, this fellow, Bill Gregory, and R.J. Robinson at the Center for Manufacturing Systems at the UK have been doing stereolithography for years. What they've been using are 3D images generated either by X-ray systems or usually MRI systems, and they have very complex software to do the splining and from slices develop three-dimensional surfaces. Okay, so all he did was to take. Fortunately, the images from Synapse were in a readable format for him. So he was able to take those images, take his software, make a three-dimensional build file, so he could then build this material. And these would be the graphites, basically. Plus, he can now interact with the model haptically. That is, you can take one of these mouses that gives you a feeling for structure and strength of a material, and you can move over the solid and then feel whether it's hard or soft using this haptic device. So you can do it that way as well. So he's taken the tomography data from Synapse that they were using to sell their systems. He uses a Z-Corp printer, and that's one of these printers that takes plastic particles, cements them together with a little glue, and makes a three-dimensional solids. And he's taken a haptic device and used all these tricks. So this is what we did. We took this data, it was 250K times magnification, and then in a process similar to how they converted normal CAT scan data, they took the data to our medical center, which is where the software happens to reside, and then they converted the slice information into a STL file using a Myra. Then it was scaled and printed on this printer, and the printer basically is a flat bed, and an arm will sweep a uniform layer of particles across the bed, and then over the top of that there will be a print head with a spray on it, which can have color to it if you want. In this case, we just kept the natural color. And every place we sprayed, that would spray some adhesive to hold the particles together. But we didn't spray, the particles would fall off. And so you build it up a layer at a time. One of the challenges is trying to figure out how big it is. Right now, I was trying to bring it today. I couldn't get in there because the lab is locked, but it's about this big. The image of this model is about this big. I've also got it next to my cell phone, so you can see how big that is. I can show you my cell phone. And so we built one. We had to build one first. It was too small. It didn't hold together. And then we did the next one. So you've already seen this particle. And there is the object. And so what's cool about this, for carbon, and I was very excited when I saw this, is look, now we can get an idea of how big the internal area is in this particle. We can get an idea of how big the pores are. Here's a pore. So now we can start to understand hysteresis in these very complex nano-sized particles by looking at a three-dimensional build model. And so I find this quite exciting because we should be able to go in here and get a pretty good guess for what the internal void volume is and approximately what the size is. if there is some hysteresis on a desorption adsorption cycle on this material, that should be characteristic of the whole size we have here. And it looks to me like we could have a really good time using this kind of system to characterize our catalysts and our porous materials at the nano level. So we're very, very excited. The next piece is, if we had a catalyst particle sitting in here, we'd like to know how big that is. Okay? And so that's what I think we're going to learn when we go to the nanotubes. We'll learn if we can get a second material imaged properly. And I think we can do that. I think we've got another picture of this as well. Yeah, so here's a picture, and again, it's about the size of that printer, and you can see a whole bunch of very interesting details. Now, you could sort of guess from looking at a cross-section of this material that there was some porosity to it, but this helps you define the three-dimensional porosity. So we're very, very excited that we can get after the fundamentals of what's happening on porous solids at the nano level. Yeah.
Now, this is all one material, that's all carbon, so it's one color of the polymer. Can you actually have the catalyst then
That's
be a
what
second
that's what we're going to find out.
Well, I can answer
Yes. Yeah.
that question. The software package also, as it's gathering the images in 3 dimensions, it can also gather data from the analytical instruments on the TEM. So you can also get your elemental compositions in this, 3-dimensional structure it's building.
Yeah, that's good.
And then once you have all that data and it's in an electronic form, you can slice it, rotate it, and really analyze a catalytic structure in great detail, and it can color the different elements, and you can see how they relate to one another in the relationships. And it doesn't matter how complex the structure is, because the electron microscope doesn't really care about that, nor does the computer.
From this one, just while we sort of talking about it, I guess you can stop the printing at any particular point and get a crosscut at that point and see hollows.
Yes, if, for example, one of the things I would like to do with the nanotube is to do a half build. I would like to build it up halfway, because we ought to see that the center is hollow. We ought to see that we have iron on the inside, and something which might start to resemble the morphology of the iron surface, et cetera, et cetera. So that, I think, would be the thing to do. Not to build the whole thing, because then you couldn't see on the inside. But exactly right. Do a half build, and look at the structure and start to see what that's doing for you catalytically. Yeah, good point. And here's another piece. There's a fine detail, and you can look in here and see the striations, and that's related to the layer by layer build. So this thing isn't, this thing has got defects in it too, because it's building up only on certain size layers. But clearly, there's sort of a characteristic pore size here that's getting into these graphitic particles that you might be able to pick up if you do an absorption-desorption experiment. You ought to be able to see something related to the hysteresis of that size pore.
The scale of that pore you indicated, what roughly are you talking about?
I was afraid you're going to ask that.
You said the soot particle?
Yeah, well, these are graphitic soot particles, is what we understand them to be. Alan, do you know the total size of that sample, the total size of that piece? Because we might be able to figure out.
The original soot particle?
Yeah. Do you remember what that was?
It might have been, half a micron, I'd say a tenth of a micron in size.
Maybe 100 microns. So this would be, so we'll have to back up. Excuse me, let's go back. We have to go back up here. So this one was the 100 microns. So this is, let's see, this is 100, that might be 20 or 30 microns. So this might be 20 or 30 nanometers. So this might be 1 or 2, 3 nanometers in that size. Okay.
I'm curious.
Yeah.
From a practical perspective, how many layers is that line, and how long did it take you to create that?
This was made, I think, overnight. Like 4 to 8 hours we'll do this. This is a little bit faster than the stereolithography. The stereolithography, you do the same thing, except you have a pool of polymer, and you polymerize it with a laser beam hitting it, and then that polymerizes. So this is done by spray coating an adhesive, and it's faster. Okay. It's not quite as detailed, but at least for a first look, I think this would be enough to show you have something close to that. But this is what they've been using in the polymers area to build fast prototypes. If you're a car manufacturer and you want to do a new door handle, you design a new door handle, you don't build the $40,000 mold, you actually generate a 3D image out of this, generate the part in plastic, attach it to the car, see if you like it, and if you do, then you spend the $40,000 to make the mold and then make 10,000. So this is the same technology that's used to make real parts, and all we've done is to use a file to start with that happens to be based on a very small image. But the image is good enough quality to give us some really interesting information. There's my cell phone. So that's how big we made it. The other thing that could be done is to, in some of this 3D visualization, put on one of these little hats and then put this in a room and walk around, and then you could walk around inside the catalyst particle. And look for your catalyst, see if any's where you think it is, right? That's the next thing we'd like to do, because we do have a visualization center on campus, but I thought this might be a little bit more realistic, and we could, start to hold this in our hands. Let's see if we have anything else. Yeah, and here's the haptic feedback tool. And I didn't get a chance to use it, but the guys who did said you could clearly, you'd go over the surface and you could feel where there was a hole or not. It would be interesting to do this then when we have different materials, because then we could code different hardnesses to the different materials and you could get a feel for that. Now, I'm not quite sure how we would use that, but at least for the catalyst particles, but anyway, it's sort of a cool thing. It's really a research thing to do.
Could you explain why the hardness? You didn't measure hardness as such. How do you get hardness?
You have to by looking at doing Alan's trick to seeing you have different materials. You would assign a different hardness to the different materials, because you now have identified the materials. So you assign the different hardness, and then you could sort of lump over it and see. You could actually put in a flex modulus for carbon. You could put a flex modulus for iron, and you could sort of simulate the difference. Like going, I'm not sure that would help us very much in this case, but you could do it. Maybe there's an instance you could think of where you could do it. Anyway, we wanted to show this because, as far as we know, this has been done. This has been modeled like this for the very first time. The company has not done this before. They just introduced the software, so we're very, very excited about using this. The software is going to be a little pricey for us, but I think we're going to try to make the investment because we think this could be very helpful to the catalyst community. And the reason I sort of jumped at talking today is I wanted to talk to some people that might actually be interested in this and see if you think this would be helpful to you, if you could do some modeling of your catalysts in this way. We need to know that. Okay? And with that, that's all I have. Hope this was helpful to you, and I appreciate the chance to talk.
Actually, I hope that we have some discussion. This is so new that we could actually, if you don't mind staying here, and see if we have some more questions.
Yeah, I put this together very quickly, and I apologize for the speed.
This is great. Actually, I was wondering, if you build it up 3D, if it's done with a transmission electron microscopy, I can understand why we can actually see inside of the particles.
Yes.
But the particles will have to be very thin in order to be transparent. So how big of a particle do you think we can actually build up and then still think that we are having inside of the model the porosity that is the true porosity of the particle?
Alan, do you have any comments on that? Alan's the microscopist, so I'll let him answer that question.
Well, you'd still be you'd have that same limitation of the TEM, which would be about 100 nanometers in thickness. You might be able to get up to 200 nanometers, but then the way to get around that is to get it to a higher voltage microscope, because the higher the voltage, the more penetration you get of the sample.
Yeah. The reason why this would be so important is because in catalysis we're always interested in pore size and measure pore volumes or specific pores and surface areas, and so this may actually be another way of helping us to have a comparative tool to some of the surface analysis that Gary does. Do you agree with that being
Yeah, I think it would be very useful for like zeolite type materials if you want to try to make a new zeolite. The only problem is a lot of times I find that when you take a catalyst and you look at it under the TEM, a lot of times the beam will damage the particle. So I don't know if you have enough time to, take all the images that you need in order to.
That's a great question. Alan, do you have an idea of what the field strength needs to be and the time period in the TEM for this kind
Yeah,
of
they were saying it would take about a couple hours to gather a series of images. And of course, this is all recorded digitally now, so I'm not sure about what sort of low-dose beam conditions you could use to minimize the beam damage. But you might be able to really turn it down to minimize that using the digital cameras.
If you've got a sample that you would like us to try, we might be able to get one more example out of the company before we have to buy the software. And we would be happy to try to do that, because I would like to see if it could be done with a catalyst. I think this is really interesting, but in terms of the practical aspect, it seems to me that it would be most useful in the catalytic field, right? That's what I think. I mean, nanotubes are nice, but I think catalysis is much more important, and you could actually use some of this to advantage. So if you have a sample that you'd like to propose, I'd be happy to try to get an image and then make a part,
But
a model.
this would presumably, if you pick up the element, you could tell the difference between cobalt and alumina.
Yes.
And so you could model a cobalt particle in an alumina sample.
Yes, and I think that's where the real value is here. I was excited to see that we could see the iron in the nanotube, and I was extrapolating that to saying, oh yeah, we could see cobalt in a catalyst particle.
If you're taking that a bit further with various promoters, you can see exactly where the promoters are.
Where did the promoter go? Yeah, where is it in the structure?
But according to Alan, we should still even go one step further and compare the oxide and the metal, right? To see if we actually have oxidation of the catalyst or not, because of the sensitivity of the TEM being.
Yeah, because it's connected to all the analytical abilities of a modern TEM, this software package, it has complete control. You can get X-ray spectra, yield spectra simultaneously along with the image data, so you'll acquire just a huge wealth of information.
So if somebody's got some catalyst samples, just one or two I could probably only do one more. So if you guys could sort of decide what you'd like us to look at.
Where do we bring it in the morning?
Oh, okay. Well, we would love to look at catalyst particles and see if we could do this, because I think this is where it would be most useful.
Would it be alright to tell the audience about what the cost factors are involved here for the software, the hardware?
Well, the software is about what, 30,000, isn't it? In that range.
Yeah, we have their original package, and to upgrade is about 30,000, and then the tomography package is another 15,000, and then you have to have a special sample holder that gives you the high degree of tilt, and that has to be custom machined, and that's probably another 20,000. And then as far as your image processing, well, we have that capability.
We have the image, what we're doing. Let me tell you what we're doing on the image processing side. I've asked Bill Gregory, who has done this for a couple of years, to put together the package that they would need in the robotics center to do this in-house. And he is in the process of doing that, and they've sort of agreed that they would fund that. We've already got the model build capability, and we've already got this fancy, printer that prints out 3D objects. So that doesn't have to be bought. All we have to do is get to purchase on the software upgrade and the sample holder and so forth. And I think that's something, if I see enough excitement here, I think that's something we can try to do at the university.
Well, we'll give you the service tomorrow morning.
Okay. But Alan and I and Bill are very, very excited about this, because we think this is pretty neat stuff, and we'd like to be on the front edge here.
the printer itself, can you maybe one more time explain? You have a powder and then
Yeah,
binder?
the printer is about, we don't have a picture of the printer here, but the printer is about 1.5 times the length of this table. And it's got a bed about so big by about so big. So it's build size. We might be able to make a model maybe 18 inches, 2 feet by a foot. That's about what you can build. And then there's a certain depth to it as well, and I'm not sure I know what that is, but it might be 6 to 8 inches up. And it's got an arm which sweeps the polymer powder across in a layer. And then it's got a print head which will inkjet spray adhesive on top. And so what you do first, let me go back to this model and let me explain how this model was built. What we did first would be to build up about 1/4 inch of a plate. So all we did was to tell it, okay, build a 1/4 inch plate underneath this model, in other words, spray adhesive on everything in this area. So it sprays that. And then we start building the morphology of this solid. So it would say, you'd have an instruction to the print head, spray here but not here. Just like you do when you do inkjet printer. This is really an inkjet printer, is what it is, with adhesive which is binding small polymer particles together. And then this is all built up. This stage is fairly fragile. If I would bring that model here and you would start to handle it a lot, you could break it. This is hardened by putting in a polymer which infiltrates the solid, and then that solidifies, and then you can get in and touch it, and you need to take dimensions or whatever you want to do, you can do that. So the sample is fairly fragile initially, but you can strengthen, and for the purpose of it is to build a 3D model that you can take up and handle. They're using this in the car industry, for example, with colors to look at where the stresses are in the part. For example, in the door handle example that we were using before, you would build the door handle, but you might say where you might put red for the highest stress area and blue for the lowest stress area. So you could see on the real part where in surface it was going to have the biggest deflection. So that's how it's being used in making parts for things like automobiles or the commodity industry. So if we would try to use color to indicate different materials. So you can make cobalt blue and iron rust colored or something. So that's how this thing works. This just goes up, builds up in layers. So you do have to design a base for it, and you do have to figure out what the 3D height is, and then sort of fit it into what you need. So this takes multiple passes.
Now, this is obviously for the TM, very thin, very small particles, very thin, 200 nanometers thick. Is it for the future applications, is there anything that we could expect that we could also do something like that for SEM?
Oh, yes, I talked to a company about that, and they said that they haven't actually connected the system to an SEM, but it's designed to work with an SEM. It's designed to work with any electron microscope, so you can have a surface. For example, if you have a surface that's used in catalytic reactions and things, you can scan the surface and create a 3D model of the surface.
Because I think that would be very important for us because we have the larger support, and we wouldn't look at that necessarily when we think of the aluminum or whatever silica support. And then just go with the next step and look for the hardest part of the step on the TM.
Yeah, if you weren't interested in, SEM, if you weren't interested in interior volume, you just need to know where the surface was. I think this would be perfectly fine. The neat thing about this for catalysis is you can see inside. Yeah, so.
But to get back like the very first picture with the wires.
Yeah.
If we want to
All you need is the wires. Yeah, you just need to know the wires,
and
don't
if
you?
we would like to see how the wires build up or see how they look like hedgehogs, but in the larger scale, we couldn't do TM because.
But you could do
obviously-
SEM.
Yeah, that's
You could do
that's
SEM.
fine.
Yeah. So yeah, I think that would work just fine.
And that would be part of the software that we have to buy.
Yeah.
You have to buy another system for the SEM to do it.
That's another 15,000.
That'd be like, you're starting from scratch. We already have a basic system for the TEM, but starting from scratch would probably be about 70,000.
Yeah, so it's money, but I think, particularly if I can see that there's some interest, we'd be quite interested in spending the money to get this capability, because I think it could be very helpful to our research.
Are there any other
Any other questions, sir? Yes.
So in the beginning of the talk, you showed some pictures of the suit.
Yeah.
You said that you slice it. Did you really
This
physically
was,
cut
yeah,
it?
no, we did not slice it physically. What happened, let me go back and, I don't think it's on here. I don't know if it's on here. Yeah. Here's an example of a slice. This would be a TEM scan, which is focused at a certain plane. Okay, so in this focal plane, you can see I've got material here, there's a hole right there. Material here, there's the top. There's another little hole here. There might be some other holes. So what you do is the software changes the focal length through the material and gives you slices. Then you need software which will take those slice images and spline surfaces, okay? Give you a 3D splining surface, which can then be put into a build file that builds the solid, okay? Building the solid from splines is done for MRI and CAT scan images right now. So all we did was to take that software with these images and build the model that you saw. Okay. So the back end of this, the building, is all known technology. We just happen to do it with new files. These files were generated by the software in the instrument.
When you showed the picture of the nanotubes, how do you know that bright part is real time particles?
Well, by experience and TEM, that's what they look like. Talk to my colleague over here, Dolly. He can explain this.
Here the image and the EDS and the EOS to detect the composition and the bonding characters. So if the error we can do the EDX and the EOS together with the same.
So you do that. You do that at the same time you're taking the scan image, and then you'll know you've got carbon and iron and cobalt or whatever it is you have, alumina. So that would be what you need to do. So you can assign a material composition to a location.
And you using the software to give the different materials different colors, right?
Yeah. Well, once you know that this material is different than another one, with the printing software, you simply say, I want the carbon to be blue and I want the iron to be black, or however you want it to come out. You simply need to specify that as a code for the printer. Okay? So again, that's all technology that's fairly well known and in hand. And all we're doing is putting in nano images and making the connections. That's all we've done. Okay?
Are there any other questions? Well, if not, then please help me thank Eric Grulke very much.
Thank you very much.
And I do appreciate that Eric put this together so quickly. This is obviously brand new, hot off the press, literally. And we hope that we can develop some proposals from that as well, and present this at the nanotechnology workshop in September. That's on September 25th in Louisville. And everyone that's on the mailing list for the Tristates Catalysis Club will get the information about this. Since we experienced at the North American Catalysis meeting in Cancun how strong nanotechnology has really taken over in the field of catalysis. So this will hopefully be presented again in September.
Well, what I can promise you at that meeting is I will have the model of the graphite particles, and hopefully I'll have the model of the nanotube with the iron in it, and so we can see, and maybe a model of zeolite. How about that?
Well, thank you very much again. And some more information about the dinner. We'll have to first meet again at the bar in the front of the entrance of the hotel and have some. That's a cash bar. And then meanwhile, I'm going to get the dinner ready for those people that signed up for the dinner. And obviously, Eric is our guest since he's our speaker. So we'll meet you back here in about 25-30 minutes. one more thing, the next meeting, I said was either the 20th or the 21st. Are there any preferences from this group right now? Anybody having a conflict that you know of? August 20th or 21st? We haven't decided. Heavens. I don't know. Anybody know?
Oh, just a minute. Well, I'm in June.
August 20th or
21st is Monday, 22nd is Wednesday, nope, it's Thursday. Thursday and Friday.
Thursday or
Or
Friday?
20th is Wednesday, 21st is Thursday, and by default, 22nd is Friday.
We haven't made the decisions yet, so if you have a conflict or so, you can email me and then I'll let you know. Our speaker is supposed to be here on both days. And then also, we have another announcement. In October, we'll be in Cincinnati, and we'll have a seminar. A representative from ETH Zurich will be giving the presentation on Dr. Robert. Okay, so